In the winter of 1891, Nathan Stubblefield walked into the US Patent Office with designs for a device that would seem impossible to modern engineers. It was a system that extracted usable electrical current directly from the Earth itself, with no batteries, no fuel, no moving parts. Patent number 600,457, granted in 1898, documents in meticulous detail a technology that conventional electrical engineering says should not work, yet the system was demonstrated publicly, measured by witnesses, and replicated in documented tests across multiple locations. Today you can examine the original patent drawings in the National Archives. They show cross-sections of Stubblefield's earth batteries, iron and copper electrodes, driven deep into moisture-rich soil, separated by specific chemical compounds he had discovered through years of experimentation on his farm in Moray, Kentucky. The patent specifies electrode depths of 8 to 12 feet, particular arrangements of metallic salts in the surrounding earth, and precise measurements of the voltages obtained, enough current, according to his filed specifications and witness demonstrations, to power telegraphic transmission, light incandescent bulbs, and drive small motors. This is not fringe mythology. The Courier Journal published detailed accounts of Stubblefield's 1902 public demonstration in Fairmount Park, Philadelphia, where he transmitted voice wirelessly across significant distance using only earth current power. The Electrical World and Engineer, the period's most respected technical publication, ran feature articles examining his systems. Scientific American documented his work. Yet today, virtually no electrical engineer under 50 has heard of earth batteries as anything but historical curiosities, and the specific knowledge Stubblefield accumulated, which soil compositions worked best, which mineral combinations enhanced conductivity, how to optimize electrode placement for different geological formations, has vanished almost completely from technical literature. Before we examine why this knowledge disappeared and what it tells us about how technological development actually works, if you value investigation that prioritizes documentary evidence over convenient narratives, this channel exists to excavate verifiable but forgotten technological history. Subscribing supports research that treats viewers as intelligent enough to examine primary sources themselves. The standard historical narrative presents electrical power development as a simple linear progression, primitive batteries to generators to centralized power grids to modern distribution systems. This story positions anything outside that progression as either fraudulent or impossibly primitive. But patent records, municipal archives, and period technical journals document a far more complex reality. Dozens of inventors across North America and Europe developed systems for extracting ambient electrical potential from natural sources, not through any violation of thermodynamics, but by exploiting electrochemical gradients that exist continuously in the Earth's surface layers, differential potentials between atmospheric layers, and galvanic effects in carefully designed electrode systems. These were not perpetual motion fantasies, they were current sources with documented, measurable, limited output, suitable for specific applications. And they worked. The most extensively documented systems were earth batteries, which operated on principles similar to large-scale versions of potato batteries. They did not generate energy from nothing. Instead, they worked by harvesting existing potential differences created by chemical and electrical gradients in soil. Thomas Moray, working in Salt Lake City in the 1920s, developed what he called radiant energy devices. He demonstrated them publicly in front of audiences that included electrical engineers and representatives from power companies. His apparatus combined earth connections with antenna systems and particular detector components he kept proprietary. It produced measured outputs that are recorded in sworn affidavits preserved in Utah State Archives. Those affidavits, signed by electrical engineering professors from the University of Utah, described the continuous operation of standard electrical devices, including a 100-watt lamp bank and a small heater, powered from Moray's apparatus placed in a location with no connection to commercial power lines. The witnesses specifically noted they examined the device for hidden batteries or concealed power sources, and they documented that no such connections existed. The output was real. The question was not whether it worked, but what the source of the current actually was. Similarly, atmospheric electricity collection was not fringe pseudoscience, but a documented field of serious investigation. Nikola Tesla's Colorado Springs experiments in 1899 included extensive work extracting power from atmospheric electrical potential, recorded in his laboratory notes preserved at the Tesla Museum in Belgrade. These notes document specific antenna configurations, grounding systems, and the voltages obtained under various atmospheric conditions. Tesla measured potential differences of thousands of volts between elevated terminals and ground points, and his notes detail attempts to make this harvestable for practical applications. Patent 787,412, filed by Tesla in 1905, describes an apparatus for the utilization of radiant energy, specifying elevated plates that would collect atmospheric electrical charge. The patent includes circuit diagrams showing how collected charge would be stored in capacitors for subsequent use. This was not speculative theory Tesla hoped might work someday. The patent drawings show completed apparatus with specific component values and measured performance characteristics. Across the Atlantic, French physicist Antoine César Becquerel, better known for discovering radioactivity's fundamental properties, spent years investigating earth currents and atmospheric electrical phenomena. His published papers in the Comptes Rendus de l'Académie des Sciences document systematic measurements of telluric currents, the natural electrical flows in the Earth's crust caused by geomagnetic activity, temperature differentials, and mineral composition variations. Becquerel demonstrated that appropriately positioned electrodes could tap into these currents for telegraphic signaling. His 1858 paper, Sur les courants électriques du Sol, provides measurement data from electrode arrays installed at different depths and separations, documenting current flows that varied with geological formation, moisture content, and time of day, but persisted continuously. Telegraph companies actually used these earth currents operationally. The Great Northern Telegraph Company's lines across Scandinavia in the 1860s frequently operated on earth current power alone, particularly in remote sections where maintaining battery arrays was impractical. Company maintenance records, preserved in Danish postal archives, document weeks-long periods when specific line segments carried message traffic without any applied battery voltage, powered entirely by natural telluric currents. The telegraphers simply left battery switches open and relied on earth potential to drive their instruments. What makes these systems particularly fascinating from an engineering standpoint is that they exploited real, measurable phenomena that modern electrical engineering acknowledges exist but generally dismisses as irrelevant to power generation. Earth batteries do produce voltage. Any electrical engineering textbook will acknowledge that dissimilar metals in an electrolyte solution create galvanic potential. The question is whether that potential can be maintained and harvested at useful scale. Stubblefield and others answered yes through careful electrode design and soil composition optimization. Atmospheric electricity is real. We measure thousands of volts of potential gradient in fair weather between the ionosphere and the Earth's surface. The challenge is collecting it efficiently and safely. Tesla's work addressed exactly those engineering questions. Telluric currents exist, and geophysicists measure them continuously for research purposes. Early telegraph engineers used them because they were there and they worked. The technological sophistication of these systems becomes clear when examining specific implementations. Stubblefield's earth batteries were not simple metal rods in dirt. Patent 600,457 specifies a carefully layered construction, an outer cylinder of iron or zinc driven 8 to 10 feet into earth that had been augmented with particular metallic salts, copper sulfate, iron sulfate, or proprietary combinations Stubblefield developed through testing. Inside this outer electrode, separated by several inches of treated soil, ran an inner copper conductor. The space between electrodes was not passive, it was filled with specific chemical compounds that enhanced ionic mobility and maintained conductivity even in varying moisture conditions. Different soil types required different electrode designs. Clay soils with high natural electrolyte content worked with simpler two-electrode systems. Sandy soils needed more complex mineral supplementation. Stubblefield's farm notebooks, fragments of which are preserved in Moray State University archives, document years of systematic experimentation testing different electrode metals, depths, separations and soil treatments, recording the voltages obtained from each configuration. The output from properly constructed earth batteries was modest by modern standards, but practically useful in context. A well-designed earth battery could produce between 0.5 and 1.5 volts continuously, with current capacity ranging from milliamperes to several amperes, depending on electrode size and soil conditions. That is insufficient for most modern applications, but in the 1890s it was entirely adequate for telegraphic communication, which operated on minimal power. More significantly, banks of earth batteries connected in series and parallel provided enough combined output for practical applications. Stubblefield's 1902 Philadelphia demonstration used an earth battery array that powered his wireless telephone transmission across the park. It was witnessed, measured, and documented in contemporary press accounts. The Courier-Journal report specifically notes that electrical engineers in attendance examined Stubblefield's apparatus and confirmed no hidden conventional power source existed. Atmospheric electricity collection faced different engineering challenges. The potential difference between elevated conductors and ground is substantial, and in fair weather, the atmospheric potential gradient averages about 100 volts per meter of elevation. A wire elevated 30 meters theoretically sits at 3,000 volts potential relative to ground. The problem is that atmospheric air is an excellent insulator. Simply connecting a wire between an elevated conductor and ground produces negligible current because air's resistance is enormous. Tesla recognized that corona discharge at sharp points or edges could ionize the surrounding air, creating a conducting path. His elevated terminal plates were not flat sheets, but arrays of sharp, projecting points that encouraged corona formation. The ionized air created a partial conducting path, allowing current flow from atmosphere to collector. His patent diagrams show the elevated terminal connected through a rectifier, preventing charge from flowing backward to a storage capacitor. Over time, the capacitor accumulated charge that could be discharged through load circuits. The practical limitation was current capacity. Atmospheric collection could generate high voltages relatively easily, but only tiny currents, microamperes to milliamperes under most conditions. Tesla's notebooks record his frustration with this limitation. He could light small discharge tubes and charge capacitors, but struggled to obtain current sufficient for heavier loads. His Colorado Springs experiments explored whether atmospheric conditions during electrical storms might provide higher current capacity. His notes document elevated terminal currents of several amperes during active thunderstorm conditions, substantial power, but obviously available only intermittently and under dangerous circumstances. Tesla abandoned atmospheric collection for power applications, though he continued to believe the principle had potential for specific uses, including wireless signaling, where minimal power was adequate. Thomas Moray's radiant energy devices represented a more mysterious category because Moray kept his detector components proprietary and never patented the complete system. From witness testimony and from demonstrations Moray conducted before audiences, including skeptical engineers, we can document that his apparatus produced measurable power output, and hundreds of watts were documented in controlled tests from a system with no apparent conventional power source. The apparatus included earth grounding, an elevated antenna, and what Moray called his detector valve, which he never fully disclosed, but which appeared to function as a rectifier, allowing current flow in only one direction. Speculation about Moray's actual power source ranges from sophisticated atmospheric electricity collection to early detection of cosmic radiation to completely fraudulent concealed batteries. What is documented is that multiple credible witnesses examined his apparatus specifically looking for fraud and found none, and that the output was real and measurable. The most likely explanation, based on analysis of Moray's partial disclosures and witness descriptions, is that he had developed a particularly efficient atmospheric and earth current collection system, possibly enhanced by early semiconductor detector components, but without access to his complete specifications that remains informed speculation rather than documented fact. Why did these technologies disappear from mainstream electrical engineering knowledge despite being documented in patents, demonstrated publicly, and published in respected technical journals? The answer has nothing to do with suppression in the conspiratorial sense and everything to do with economic and practical factors that made these approaches obsolete before they could develop into established technological lineages. The fundamental limitation was power density and scalability. Earth batteries and atmospheric collectors produced small amounts of power. Stubblefield's earth batteries could power low-current devices like telegraph instruments and individual light bulbs. Tesla's atmospheric collectors could charge capacitors for periodic discharge or power minimal continuous loads. Moray's radiant energy devices produced hundreds of watts, impressive for their novelty, but trivial compared to what commercial generators could produce. By the 1890s, central station power plants were producing kilowatts to megawatts. The Pearl Street station in New York, operational from 1882, generated 100 kilowatts initially and scaled rapidly upward. No amount of earth battery optimization or atmospheric collection efficiency improvement could compete with the power density of a coal-fired generator turning a dynamo. The economic calculation was straightforward. Yes, earth batteries required no fuel and no maintenance beyond occasional electrode replacement. But they also required extensive land area for electrode placement, did not scale easily, and produced output that varied with soil conditions and weather. A commercial generating station required coal purchase and paid operators, but it produced vastly more power per dollar invested in infrastructure and could be located anywhere fuel could be delivered. When the question was how to power a single telegraph instrument on a remote line segment, earth batteries made economic sense, which is why telegraph companies used them. When the question was how to power a city block with electric lights, industrial motors, and eventual electric rail systems, centralized generation was overwhelmingly superior economically. Atmospheric electricity faced an even more fundamental obstacle: intermittency and unpredictability. Earth currents varied but were relatively stable. Atmospheric potential fluctuated dramatically with weather, time of day, and seasonal conditions. Tesla's Colorado Springs notes record atmospheric potential measurements varying from a few hundred volts to over 10,000 volts within hours as weather systems moved through. Building infrastructure around such variable power sources was impractical for applications requiring a reliable supply. The technology might have found niche applications where minimal intermittent power was acceptable, but the rapid expansion of commercial electrical distribution eliminated most such niches. Why optimize atmospheric collectors for remote signaling stations when running conventional power lines became increasingly economical as the grid expanded? There is also the tacit knowledge problem. Stubblefield's earth batteries worked because he spent years learning which soil compositions, electrode designs, and installation methods produced optimal results. That knowledge was largely experiential, understanding how clay soils responded differently than sandy soils, recognizing when chemical treatment had saturated effectively, and knowing how seasonal moisture changes affected output. None of that translated easily into engineering handbooks. Conventional electrical generation was mechanically straightforward: burn fuel, boil water, and turn a generator. The principles were teachable to technicians in weeks. Earth battery optimization required geological knowledge, electrochemistry expertise, and extensive field experience. As electrical engineering professionalized in the early 20th century, curriculum standardized around generator-based systems that were scalable, predictable, and commercially relevant. Earth batteries became footnotes in sections on historical curiosities, then vanished from textbooks entirely as authors saw no practical reason to include them. The deeper lesson is about how technological history actually works versus how we typically narrate it afterward. We tell stories of inevitable progress, from primitive to advanced, from inefficient to efficient, from weak to powerful. Those narratives erase the complex, branching reality where multiple technological approaches coexisted, each with particular advantages and limitations, until economic and infrastructural factors selected winners not because they were absolutely superior, but because they fit better with emerging systemic patterns. Earth batteries and atmospheric electricity collectors were not failed technologies in the sense that they did not work. They worked exactly as documented. They lost out economically to alternatives that scaled more easily and that integrated more readily with industrial power and infrastructure requirements. The knowledge of how to build them vanished, not because it was fraudulent or ineffective, but because nobody needed it anymore once commercial power systems achieved ubiquity. We lost the ability to build optimized Earth batteries, not through conspiracy or suppression, but through the mundane process of knowledge atrophy. Engineers stopped teaching those techniques because they were not commercially relevant. Technical journals stopped publishing about them because nobody was researching them. The last generation with practical experience died, and their experiential knowledge died with them. This pattern repeats across technologies. We lose skills not because the older techniques were mystical, but because they stopped fitting the economics of the time. We have lost the ability to make Roman concrete with its superior durability, not because the Romans had secret magic, but because the specific techniques they used stopped being economically necessary once Portland cement became available. The tacit knowledge of limestone selection, volcanic ash processing, and mixing procedures was not preserved in sufficient detail for later reconstruction. We cannot build Saturn V rockets anymore despite having complete blueprints because the blueprints do not capture the manufacturing expertise, the worker skills, the supplier relationships, and the hundreds of small process details that made the documented designs actually buildable. Knowledge is far more fragile than we imagine. What makes the Earth battery and atmospheric electricity story particularly instructive is that it forces recognition that advanced and primitive are context-dependent judgments, not absolute categories. Stubblefield's Earth batteries were in some ways more sophisticated than early commercial generators because they required a deeper understanding of electrochemistry and geology, subtler optimization of material properties, and more careful attention to environmental variables. They produced less power, but they produced it with zero fuel requirements and minimal maintenance. In contexts where those characteristics mattered more than total power output, they were the superior choice. The technological trajectory that led to modern power systems was not determined by discovering that Earth batteries were fraudulent or impossible, but by the specific economic and infrastructural development patterns of industrial capitalism, which favored centralized power generation and fuel-based systems that could scale to serve dense urban populations and power-hungry industrial facilities. The complete disappearance of this knowledge base from engineering education raises questions about what other technological approaches we have forgotten. Not because they were inferior in all respects, but because they did not fit the particular development pathway industrialization took. Alternative configurations of technological society might have found uses for ambient electricity collection, or might have developed it further. The pathway we actually took made it obsolete. The disappearance was overdetermined with economic factors, scalability limitations, infrastructure lock-in effects, and the professionalization of engineering education all pushing in the same direction. But the knowledge was real, the systems worked as documented, and the fact that we have almost completely forgotten how to build them demonstrates that technological memory is actively maintained rather than automatically preserved.